Hi and welcome to this inferential statistics video, which is covering the 95% confidence interval for the population proportion. So in this video, we're going to revise the 95% confidence interval for the population proportion, which is part of the Inferential Statistics course. Before you do this, it will be a good idea for you already to have revised z-scores because we're going to touch a little bit on that, and also for you to have revised the 95% confidence interval for the population mean. And that video is linked below, as well as the video on z-scores. And there is a full video which covers the complete inferential statistics course, and that has also been linked in the description below. So now we're going to talk about the 95% confidence interval of the population proportion. So just like with the mean, we can use the information we know about the sample proportion, p hat, to create a 95% confidence interval for the population proportion, p. This is a range of values that we are 95% sure the population proportion sits between. To create the range, we're going to use the standard error of the proportion that we find on page 34 of our log tables. However, because we don't know p, the proportion, we're going to use p hat instead. So what that looks like is, for the 95% confidence, we are going to start, I'll work it through and then I'll give it to you properly. We'll start with p hat. So that's from the sample, it's the proportion, but we know that the proportion from the sample is never going to be as accurate as the actual population. So it's going to be the proportion give or take. Give or take, so that's going to be plus or minus some piece. Because we're dealing with 95% confidence, we're going to talk about 1.96, and the piece in this case, so give or take 1.96 times this piece, that is going to be the standard error of the proportion. Because I won't know p, I'm trying to do the interval for p, we're going to use p hat in this formula instead, and it will look something like that. Now, when we actually break it down, I would advise you to write it with less than or equal to signs, and it will look something like this. So p hat minus 1.96 times the standard error of the proportion is less than or equal to p is less than or equal to p hat plus 1.96 times the standard error of the proportion. So let's take an example. Just like all the other questions, we're going to read through and label where we can. Just be aware that when we're dealing with the proportion, that some of the numbers may not relate exactly to a single value. So for example, we may not get p hat directly, we may have to calculate it. So a company surveyed 400 people. So we're saying that we see the word surveyed, so we know we're in a sample. 400 people is my n. And they're chosen from the population of people who bought at least one chocolate crunch bar. Of those surveyed, 324. Now, that is not p hat, because p hat means the proportion or the fraction or the decimal or the percentage of people. So when I deal with proportion, we're going to always want to find a fraction of people. So it's not going to be 324. It's going to be a fraction less than 1. So we're going to have to hold that for a second, and we'll come back. So it asked me to create the 95% confidence interval for the population proportion who liked the new bar. Give your answer correct to 2 decimal places. Okay, so I'm going to start with my formula, because if I write down my formula, at least I know where I'm going. So I have p hat minus 1.96 because we're in 95% confidence, and this is the standard error of the proportion. P hat times 1 minus p hat all over n, less than or equal to p, less than or equal to p hat plus 1.96 square root of p hat 1 minus p hat over n. Now the 1.96 is multiplied by that standard error of the proportion. So all I'm looking for is p hat. So p hat is the sample proportion. So they told me, again, let's go back to the two numbers I underlined. There are 400 people in my sample, and 324 of them said they liked the new bar. So we can actually use that to create the fraction of people in my sample who liked the bar. But generally when we're dealing with this formula, it is much easier if possible, to work with decimal. Now, we won't always be able to work with decimal. If the decimal is a bit awkward, obviously you're better to keep it more accurate. But for us, in this case, it's absolutely fine. It works out as 0.81. So what this formula looks like then is 0.81 minus 1.96 times 0.81 times 1 minus 0.81 all over n, which is 400. So I should have written that here so it's really clear for anyone correcting my work. Less than or equal to p, less than or equal to, I'm going to just move down here for a bit of space, 0.81 plus 1.96 square root of 0.81 times 1 minus 0.81 all over 400. And at this point then you can put that straight into the calculator to work out the population proportion. So working the first part, we get 0.7716 is less than or equal to p is less than or equal to 0.8484. So it just said to us, create the 95% confidence interval for the population proportion who liked the new bar. Give your answer correct to 2 decimal places. Now, for 2 decimal places, we'll have 0.77 is less than or equal to p is less than or equal to 0.84. So we're going to do another example of working backwards. So in a poll carried out by a rival marketing and research company, a sample of X voters, so I'm just going to highlight as I go, X voters was surveyed. 60% of the sample, okay, so they've given us out straight that this thing here, 60% of the sample, it is p hat, claimed that they voted in the last general election. A 95% confidence interval for the proportion of voters who said they voted was this. Calculate the number of voters who were surveyed. So we will first of all look at our formula, and we have p hat minus 1.96 square root of p hat times 1 minus p hat all over n is less than or equal to p is less than or equal to p hat plus 1.96 standard deviation of p hat 1 minus p hat over n. Remember, that's the standard error of the proportion taken straight from page 34 of our log tables. So we know p hat, and we can work with either side of that to figure out what n was. Now, the thing is, we can simplify this slightly. So yes, we know that p hat is 0.6, and that's great. So I could just take this side here and say I have 0.6 minus 1.96 square root of 0.6 times 1 minus 0.6 all over n, and that should give 0.55706, and I can work with that. Now, we did a similar example with regards a confidence interval of the proportion mean, where we actually subtracted the numbers and just worked with the extra plus or minus piece. Now, absolutely fine to do that here as well. However, because we know p hat, it is just as easy to work through without any subtraction. So let's clean up what we can. So we're going to have 1.96 square root of 0.6 times 0.4 all over n, and I'm taking 0.6 from both sides, which will give me on this side minus 0.04294. So the next step will be to divide both sides by minus 1.96, and what we're going to get, I've run out of space, I'll clear it in 1 second. So we have 0.6 times 0.4, that's 0.24, all over n is equal to 0.55706. 0.021908. Okay, so I'll just clear this and we will continue on. So if you need a second, maybe pause the video to take down to here before I clear the screen. So from this line here, what we're going to do is we're going to square both sides to get rid of our square root. And we get 0.24 all over n is equal to 0.021908 squared. We can flip both fractions. That gives me n over 0.24 is equal to 1 over 0.021908 squared. You can square that out if you want. I'm just going to wait till the end to show all my calculations. And then I'm going to multiply both sides by 0.24. So I have 0.24 all over 0.021908 squared. And putting that into the calculator should get us our value for n. And we get in around 500, it's 500.04, which has just got to do with our rounding. So the number of voters who were surveyed was 500. So now let's work a little more with proportion. And an interesting little question here from the actual exam papers, linking in with a little bit of calculus. So it says, using calculus or otherwise, find the maximum value of p hat times 1 minus p hat. So I'm going to start this as a y, and I'm going to have p hat times 1 minus p hat. Now, you can work with the product rule here. However, what I'm going to do is I'm going to multiply that out, and I get p hat minus p hat squared. So using the rules, and the rules of calculus, which are found on page 25, we know that we bring down the power and take 1 away from the power. So imagine that p hat is like an x will go to 1. So this is, dy dp hat. And then here we bring down the power and we take 1 away from the power. So we get that. So when we differentiate it, we end up with 1 minus 2p hat. Now, if it helps, you could think of it in terms of x's. So we would let x equal to p hat, x times 1 minus x. You get x minus x squared. And therefore dy dx is 1 minus 2x. But I know x is actually p hat. So I get to the same answer. So if you want to kind of work with x's, that's a way that you could. Now we want to get a maximum value. So for the maximum, we let the derivative 1 minus 2p hat equals 0. Again, you can leave it as x if this is too confusing. And we get minus 2p hat is equal to minus 1. So p hat is minus 1 divided by minus 2, which is a half. So the maximum value of p hat 1 minus p hat will be, so the maximum will happen when we have p hat is equal to half, so 1 minus a half. So it'll be a half times a half, and the maximum value will be a quarter. So this is linking into what we've already done in calculus with regards differentiating, letting it equal 0, finding the max value of usually x, and then subbing it back to find the function itself. But it's doing it with our p hats. So I'm just going to again clear the screen just to work with the next part.